Okay, I think that should be good. Hello, my name is Patrick Duke. I'm a PhD student at the University of Victoria, and I'm giving the first MEOPAR webinar of 2020 in collaboration with Canada's Ocean Acidification Community of Practice. You can find them at oceanacidification.ca. I'm currently presenting from Coast, Straits Salish, and Esquimalt territory here in Victoria, BC. And today I'm just going to be touching on ocean acidification sensors. We're going to be going over some commercially available options that are out there and some considerations to take when purchasing sensors for your project. So first, we're just going to start with what is ocean acidification. Here's a definition from our partners south of the border at NOAA. Ocean acidification is occurring because our ocean is absorbing carbon dioxide from the atmosphere, leading to lower pH and greater acidity. This is causing a fundamental change in the chemistry of the ocean from pole to pole. So you can see here from the NOAA Observatory in Hawaii, atmospheric concentration of carbon dioxide is steadily increasing over time with anthropogenic inputs. The partial pressure of CO2 in seawater at the surface is paralleling that increase, and seawater pH is steadily declining, causing greater acidity. Well, what's being done about this? Many groups, including ours at the Community of Practice, are aligning with the United Nations Sustainable Development Goal number 14, Life Below Water. Under 14.3, the United Nations hopes to minimize and address the impacts of ocean acidification, including through enhanced scientific cooperation at all levels. This means we hope to observe ocean acidification, identify the drivers and impacts of ocean acidification on marine ecosystems, and provide biogeochemical data to optimize ocean acidification modeling and predictions. All of this starts, of course, with that observing component, and that's where sensors come in. Autonomous sensors are now widely used in ocean monitoring efforts, as they've made substantial gains in recent years, including in both accuracy and precision, while lowering costs, making them more accessible to researchers, industry, and community leaders. Deployments include sensor integration on offshore open ocean moorings, coastal estuary moorings, monitoring platforms, some cabled like the ones on the Canadian coast through Ocean Networks Canada, as well autonomous underwater and surface vehicles like profiling gliders or wave gliders, as well as profiling applications like your CTD Rosette systems, as well as biogeochemical Argo floats. Sensors offer an increased temporal resolution and the ability to resolve variability compared to occasional field measurements. The resolution that sensors are able to collect over deployment intervals is something that field measurements could never capture or would cost an absurd amount. So currently, autonomous pH and PCO2 sensors are the furthest along in ocean acidification sensor development. And we're just going to be touching on a handful of ocean acidification sensors that are available. We're going to be looking at how they work, what they can be used for, and we're just going to start with pH sensors. So the YSI probe is a commercially available sensor using the glass electrode method to measure pH. So it's measuring the electrical potential of a solution between two electrodes, with the glass electrode referenced against a solution of stable pH. So the YSI is capable of operating within a wide range of environments, looking at that operating temperature, the operating salinity, and the pH range that it's able to measure. But the accuracy is lower compared to some of the other sensors that we're going to touch on. The response time is quite fast, but the important part about sort of that makes this unique is that it integrates with a multi-parameter water quality instrument. And the full sort of 7-sensor suite with all the gadgets that you need to make it usable comes in at a relatively low cost. The idronaut 311 uses a gas electrode method as well, same as the YSI. The probe is very user-friendly and with just a single buffer for user calibration. It also easily integrates with third-party CTDs, so can be sort of configured to integrate with the monitoring systems that your lab may already have in place, or the sensors that your lab is already pretty comfortable operating. The environments here, capable of operating pretty extreme environments. The operating temperature, operating salinity, and the pH range are quite good. The accuracy as well is quite good with that same response rate as the YSI. But one thing to note here is that drift. So this can be a concern over very long deployments. But that price point does make it pretty accessible and the cost is quite low. So the CFET uses a ion-sensitive field effect transistor to measure pH. So this means there's two independent electrodes. One is an external solid-state chloride ion-sensitive selective reference electrode, and an internal silver-silver chloride reference electrode. So both are electronically identical apart from the reference type. And the conduction channel of the transistor is covered with an insulator that has a surface coating. The surface charge of this coating is dependent on the pH of the solution that it's exposed to. So changes in solution pH then alter the potential on the conduction channel, which allows ocean pH to be measured. The accuracy here is quite good. The response time is very fast. Operating salinity, temperature, pretty accessible for most environments. As well, the plastic housing is more for your surface application, but then there is this sort of deeper housing integrated with an oxygen sensor for your 2,000 meter depth. The drift here as well, it is better than the idronaut, but that improved drift is coming in at a price point that is above what the idronaut would be. SMAI from Sunburst Sensors measures pH by absorbance. So the SMAI pH sensor flushes sample seawater through its flow cell to establish a baseline absorbance, then injects a coulometric pH indicator. This is pumped through the flow cell and absorbances are measured, and the pH can be calculated at each sort of pump or injection of this indicator as it perturbs the pH of the sample. And the regression of the indicator concentration versus pH is used to calculate the actual sample pH. So these have some of the highest quoted sensor accuracies. And the environment can operate in most. There's also this sort of your standard housing for, again, surface to moderate depth applications, and then there's this titanium housing for your deep applications. The important thing with the SMAI is that it does not suffer from drift like the idronaut based on the glass electrode method, or the CFET based on the ion selective field effect transistor pH measurements. And that's because of this spectrophotometric pH measurement method. This response time is a little bit slower, and that's because this method does take some time. But the price point is comparable to the CFET. The ISAMI pH is based on the same technology as the SMAI pH, using that spectrophotometric coulometric reagent method, but it's exclusively meant for surface applications. So this is your 0 to 3 meter depths, very close to the surface, and it's very inexpensive. So this price point includes a accessory battery that allows this sensor to operate for an 160-day deployment interval. The accuracy is still quite good, and response time can be slower compared to the CFET due to that spectrophotometric method. Moving on to PCO2, or partial pressure of CO2 instruments. So here is the SMAI CO2, again from Sunburst Sensors. So this uses a spectrophotometric pH method similar to the SMAI pH to determine PCO2. So here it actually pumps a coulometric pH indicator into a CO2 permeable membrane where it equilibrates with the seawater sample. This equilibrated indicator is then pumped through a detection cell, and the solution absorption is measured at wavelengths that correspond to known absorbent frequencies of the indicator. So the ratio of absorbance, along with some reagent chemistry, allows for the generation of the calibration curve and the determination of PCO2 in situ. So this method does result in a relatively slow response rate, again, due to that spectrophotometric method, but the accuracy is quite good. And again, these sensors do not suffer from drift. So if you're looking for these long-term deployments, this is a very good option. And the operating temperature is below actually what that SMAI pH sensor is capable of operating. So you can get down to those Arctic temperatures if you're looking for a deployment in the north. Price point comes in pretty average for what we're going to see these PCO2 sensors sitting at. So now sort of flipping to the infrared absorption spectrometry method. The first one we're going to talk about is the Subseatec PCO2 buoy and their analyzer as well. So this just uses infrared absorption spectrometry, which means surrounding seawater equilibrates with gas contained in a chamber internally to these sensors through a gas permeable membrane. The CO2 concentration are then measured optically using non-dispersive infrared absorption spectrometry. And the Subseatec buoy can be calibrated with standard gases in situ. But there also is an internal zeroing, where sort of internal gas can be circulated through a CO2 scrubbing system, where you can get sort of interval zeroing to sort of account for that drift over those longer deployments. One of the other things that I should mention with Subseatec is they really specialize in these tailored solutions. So that MK2 analyzer is actually more for underway systems, which we don't touch too much on today, but here is one where they actually house that analyzer in a sort of carbon fiber frame, and it's developed for racing sail yachts. So that's something to consider if you have sort of a crazy ask. I think these guys might be able to put it together, but that, of course, does come at a cost. So that price point is going to be higher than you're going to see for the SMAI or for the Proceenus, which we're going to touch on next. But that also was higher because you do get a LiCor infrared gas analyzer inside both of these instruments. So the Proceenus CO2 Pro. So again, this is using that infrared absorption spectrometry method, and it's fairly comparable to what you saw previously as respect to response time and accuracy, but the sort of the big component here is the operating temperature that these things are capable of being deployed in is very tailored to the environment that they're going to see. So that's something to consider if you're working in sort of these regions where you're expecting extremes. This is a sensor where it will likely do quite well. And the price point is about the same as what we saw with the SMAI CO2 from Sunburst. One more sort of thing I wanted to touch on. This is the last sensor package. This is from Proceenus CO2 Pro Atmosphere. So this is, again, reliant on that infrared absorption spectrometry method, but this is specifically built for surface buoy deployments or autonomous surface vehicle integration. So they're looking at an operating temperature same as the CO2 Pro, sort of tailored to a handful of different environments. And again, just like the Subseatec and the CO2 Pro, there's that internal zeroing during deployment to help correct for drift. But drift is something to be aware of in these infrared absorption spectrometry sensors. Accuracy, pretty comparable. Response time in the water, it's going to be a bit longer than what you see in the air. And the price point, because of that integration with, it can measure both PCO2 in the atmosphere and PCO2 in the ocean surface, it's going to be coming in a little bit higher than your standard CO2 Pro instrument. So of course, if you're going to purchase any of the sensors that we got to talk about, you're going to want to couple those ocean acidification sensors with a CTD. So then you can get temperature and salinity measurements. Consideration should be taken to some redundancy. If you can deploy, 2 pH sensors, that would be great, or 2 PCO2 sensors, or even coupling with a biogeochemical sensor, putting a pH and a PCO2 on board, or including an oxygen sensor would be great, so that you can kind of see how these things behave relative to a more mature technology in the oxygen. But with just CTDs, if you are looking to just measure, ancillary temperature and salinity, there are options out there from RBR, from Seabird, as well as some low-cost options like the Castaway CTD from Xylem, the same group that makes that YSI probe we touched on first. So this is the sensor setup I recently got to work on. This is a community observatory in Cambridge Bay, Nunavut, and I was evaluating sensors sort of stressed to possibly the edge of their environmental tolerances. So this is Arctic deployment. You're seeing that, minus 1.5 degrees seawater for most of the year. You're under sea ice for most of the year. And this is important because no matter where you deploy these sensors, however harsh the conditions are, you do want to be taking validation samples throughout the deployment to detect for drift or offset, and then be able to correct for drift or offset. And some conditions are more extreme than others. You can see in the fall, and then in the winter, in January, it's pretty tough. In the spring, during breakup, logistically can be difficult if you're testing this in the Arctic. Or in the summer, or if you're working in open water seasons, things can still be hard given the weather, or even just getting out to the site where these things are deployed, or even if you're close to shore, it can be tough. But getting those discrete samples collected throughout the deployment is extremely important if we want to try to mature this technology by making those calibrations throughout the deployment, and not just when we put it in the water and when we pick it up. So now just some considerations to actually take when you're selecting what to use or what to purchase. The very first thing, obviously, is budget. What does your grant allow, or what does your company allow you to write off, or if you're a community group, what sort of funding can you get either from government or from industry partners to sort of fund your monitoring efforts. And then the next thing is, what are you going to be using it for? Is it a profiling application or a moored application? If it's moored and it's sort of sitting at the same depth throughout the entire deployment, then response time might not be so much of an issue. But if you're profiling and your sensor package is moving up and down the water column, then you're going to want something that's a little bit faster to capture that variability as your wave glider or Argo float or Rosette is moving through the water column. Or also something we didn't really touch on is underway systems, but all those companies, Subseatec, Proceenus, they all offer underway flow-through systems for shipboard measurements. So depending on how big your porthole is, or what sort of flow rate you expect to just installing this into another ongoing underway system, those are something to consider with which sensor to integrate. The third thing is this environmental conditions. You saw that a number of sensor companies are offering sort of different housing for their sensors to work and operate properly in a variety of different conditions. And sort of, if you're putting something in the Arctic, you probably want something rated to -2 degrees. Pumped versus unpumped. So this is something to consider. If your system is unpumped, response time is usually faster and battery consumption is quite a bit less. If your sensor system is pumped and it's moving water through the system actively, that takes power and it slows the measurement down. So your response time is going to be a little bit slower, you're going to be consuming battery, and that's something to consider if you are reliant on a battery source that is directly connected to the instrument and you're not cabled and don't have to worry about that stuff. So sort of building that battery budget. How long is your deployment? Which is the next point. Deployment length. So you want to consider the sensors that are going to have less of a drift factor if your deployment is going to be longer. Something like the ISAMI from Sunburst, right? Drift is not so much of an issue over those very long deployments. Anti-fouling. So if biofouling is a real issue in the region that you're going to be putting these sensors, then anti-fouling measures might be something you want to consider. Talk to the manufacturer, let them know where you're putting it, what you expect, and if biofouling is an issue, there are solutions that can be made. The last point here is recognize that these sensors are not mature. This is really important. Ocean acidification sensors and carbonate system sensors are just not as far along as some of your temperature and salinity sensors, or even your biogeochemical sensors in oxygen, with quality assurance and quality control measures, even data and metadata output. Those things are a little bit, they're in development, and we're going to touch on that later. So to kind of conclude our sensor section, recommendations for long-term marine sensor deployments. Number one, appropriate pre-deployment sensor conditioning periods. The manufacturers will communicate whether this is necessary, but some of these sensors need to be in like conditions to what they're going to be deployed in before they actually get deployed and sort of get to sit in that and adjust to those conditions. And that's important if your sensor requires that. Number two, collection of frequent discrete samples throughout deployment. So this is that validation of the sensor throughout the deployment. You're going to want to collect one when you put it in the water and one when you take it out for discrete samples to sort of validate where the sensor is at those endpoints. But if you can collect frequent discrete samples throughout deployment, that would really enhance your data set and show that these sensors are working properly, and also sort of help mature the technology as you share that data with people that are working on this stuff. And then number three, we mentioned before, co-located marine biogeochemical sensors. Of course, you want to have temperature and salinity sensors on board, whatever your application is, but co-locate a PCO2 with a pH sensor, or have some redundancy in two pH sensors, or try to include an oxygen sensor if that's possible, or if the budget allows for it, or your battery budget does as well. So now I'm just going to touch on a few things that relate to these sensors, but that was published recently in an article in Frontiers in Marine Science, Perspectives on In Situ Sensors for Ocean Acidification Research. This is really about the sort of back end of these sensors in data. So the first sort of question that this paper tried to answer was, what are the factors limiting the precision and accuracy and reliability of sensor data? And most instruments have been developed and tested under conditions of moderate temperature, relatively constant salinity, typical of temperate oceanic waters, possibly limiting deployments in more extreme environments. This is slowly shifting, as you saw some of the sensors I presented. Pro Oceanus had lots of offerings in extremely warm tropical environments as well as very cold Arctic environments, and other sensor companies are quick to catch up on this because those extreme environments are likely where we're missing observations. Assessment of in-situ sensor performance should incorporate sensor redundancy and include pre- and post-deployment laboratory calibrations. So sensor redundancy, yeah, put 2 pH sensors in if you can. Include biogeochemical sensors. But this pre- and post-deployment laboratory calibration, if your lab isn't capable of doing this, or if your group isn't capable of doing this, then be sure to include the manufacturer in this and try and see if they can do that pre- and post-deployment calibration if it isn't already included in what you paid for when you got the sensor. The second one was, what can we do to facilitate the quality assurance and quality control processes that optimize the utility of these data? So QAQC best practices for carbonate system sensors still require a lot of work to meet the same standards as more mature sensors, like I mentioned, oxygen. But this takes a community effort. You need to be sort of sharing what you're doing and how you're progressing this with each deployment. So ocean best practices repositories archiving best practices submitted by individual authors and groups with an objective of developing community best practices. There is a carbonate system sensor section to this, and I strongly encourage you to submit what you have to ocean best practices. Also, Fix03, they have a handbook for best practices. Quality control procedures for carbonate system sensors are not ready to be adopted as best practices just yet, but the handbook does have some ideas, and further work is required, and that's where that community effort really comes in. One of the things that's helping sort of facilitate all of this work and sort of this community effort is the Ocean Acidification Information Exchange, which I'll touch on later, but that's one sort of forum to share what you're doing. So this is the last point from the paper. What sort of data or metadata are needed for this data to be most useful to future users? So as with QAQC best practices, data archiving and metadata requirements are not standardized. They vary largely with individual manufacturers' output streams. This is an issue. If we want to try to streamline these things into a sort of accessible means for modelers and touch on that Sustainable Development Goal 14.3, which had a component of sharing biogeochemical data with modelers to improve ocean acidification models regionally and help improve prediction, then this is going to be something that has to sort of move further along. Models and recommendations for ocean sensor metadata have been developed. There are templates out there. GoOn, SOCAT serve as starting points for more universal standards. Another resource is OCADS. They have a data submission portal which provides a bit of a template for carbonate system metadata requirements. Take a look at those, see if they're appropriate, if you think they're appropriate, and then be sure to share and try to update these things as it is a community effort. So just a couple sort of takeaway points for scientists and PIs, and then we're going to touch on a couple of takeaway points for community groups if you're tuning in as well. So for a couple science action items, number one, for these sensor manufacturers and people that are doing the research on sensor development, creating more affordable sensors that can function in a complex coastal zone experiencing multiple stressors needs to be a priority for future observing needs. This is where we have limited monitoring, where ocean acidification is projected to be some of the most extreme, and this includes in the Canadian North as well. So for observational scientists, the sort of action item is long-term and accessible field observations are critical for modeling and need to be maintained. Again, Sustainable Development Goal 14.3, if we want to inform modelers and models to help get better projections of regional ocean acidification in the future, then these long-term field measurements are very helpful, but also making them accessible and thinking about that data quality assurance, quality control data sharing and metadata sharing to really sort of streamline how we share this and get this data accessible to modeling groups. The third point is promote co-production of research by actively involving different sectors of society. This includes industry, so the shipping industry, commercial shipping industry, also public ferry transport. All of these offer great sort of platforms for underway systems to be installed and data to be collected. But one of the most important ones is Indigenous populations. Canada's Indigenous populations are sort of at the forefront of climate change and ocean acidification if they're a coastal community, and those groups need to be involved in this discussion and need to be involved in the co-production of knowledge around ocean acidification that will impact their communities. And then the fourth point, while adaptation and conservation are important, reducing CO2 emissions globally should remain the priority to address ocean acidification. Take an active role in trying to inform policymakers on reducing CO2 and sort of the impacts that climate change can have, even if you're in the interior of Canada and not on a coast. This is still a priority. Sort of the last piece here for community action, students, community groups that are following along. The first one, work with informal educators such as aquarium outreach programs and local nonprofits to teach the public about acidification. The more you share your research and why you're doing your research and what sort of the importance of your research is around ocean acidification, the more people will care and the more this will sort of get the ball rolling in how people vote. The second one, participate in habitat restoration efforts to restore habitats that help mitigate the effects of coastal acidification. Parks Canada has programs to get students involved in these restoration efforts. Reach out, see what you can do. Anything that is a sort of a net carbon sink ecosystem is something that is important and needs to be maintained. The third one, facilitate conversations with local businesses that might be affected by ocean acidification and building a plan for the future. So all of your aquaculture or fishing industries and companies along the coast, make sure they know what the impacts of ocean acidification could be on their business and make sure they have a plan for that. Just get the ball rolling with these conversations and then bring in people as you need them to sort of further that in development. And then the last one, partner with local community efforts to reduce CO2 emissions, support local agriculture, bike and car shares, and other public transportation options to work, and take an active role as a voter. Write your counselor or your MLA or your MP about the importance of reducing CO2 emissions, because that's ultimately the best thing that we can do to mitigate the effects of ocean acidification. So just a couple of resources that I touched on: oceanacidification.ca, of course, oceanacidification.noaa.gov for all the stuff in the U.S., and the Ocean Acidification Exchange, the Information Exchange. So join our Canada team on the Ocean Acidification Information Exchange. There's lots of updates. People are working some pretty cool stuff, and this offers a great sort of forum to talk about these things and work through them together, as well as go on for the sort of global ocean acidification perspective. And you can see the paper that I touched on here at this DUI. If you're looking to purchase any of these sensors, here's all those manufacturers' websites. I'm sure they would love to get in touch and talk you through more than I was able to talk you through. But here's my email as well if you have any questions for me, if you're checking this out after the webinar. But thanks so much. Thanks so much for having me. Take care.